Preparing for a software engineering at JPMorgan interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you solve the two-sum problem, and what is its time complexity? I would solve the problem with a hash map storing each value's complement as I scan the array once. For every number x, I check whether target minus x already exists, then record x if needed. This gives O, n, time and O, n, space, versus the O, n squared, brute force approach. I would clarify whether duplicate values are allowed and explain integer overflow handling when constraints are large. While answering, explain the brute force baseline, hash map optimization, complement lookup, duplicate handling, complexity analysis, and how you would clarify input constraints before coding. Question 2. Explain the difference between a process and a thread, and when you would use each. A process has its own address space, while threads share memory within a process. Processes provide stronger isolation but require more resources and inter-process communication. Threads are lightweight and efficient for parallel tasks, though shared state introduces race conditions. I would use processes for fault isolation or independent services, and threads for concurrent work inside one service. In Java, I would combine thread pools with synchronized access or concurrent collections. Make sure to cover memory isolation, execution overhead, shared state, context switching, synchronization, failure impact, and practical examples involving concurrent transaction or service processing. Question 3. What are the key principles of object-oriented design, and how have you applied them? Object-oriented design organizes behavior around responsibilities rather than scattered data manipulation. I use encapsulation to protect invariants, abstraction to hide implementation details, and polymorphism to replace conditional branching. I generally prefer composition over inheritance because composed components are easier to change and test. For example, a payment service can depend on a payment processor interface while supporting card and bank implementations. Solid principles help keep those dependencies focused. In your answer, discuss encapsulation, abstraction, inheritance, polymorphism, composition, solid principles, testability, and an example where design choices reduced coupling or simplified future changes. Question 4. How would you design a thread-safe singleton in Java, and would you recommend using one? My preferred implementation is usually an enum singleton because Java guarantees one instance, safe publication, and serialization protection. If lazy initialization is required, the initialization on demand holder idiom provides thread safety without synchronization on every access. I would still question whether a singleton is appropriate. Global state complicates testing and hidden dependencies. In a service, dependency injection normally gives clearer lifecycle management and makes collaborators replaceable. Be sure to mention lazy versus eager initialization, class loading guarantees, double-checked locking, volatile, dependency injection, testability, and why global mutable state can create design problems. Question 5. How would you investigate and fix a slow SQL query used by a banking application? I would first capture the exact query, parameters, latency distribution, and database load. Then I would inspect the execution plan for full scans, expensive joins, poor cardinality estimates, or sorting. I might add a selective composite index, rewrite predicates, reduce returned columns, or batch requests. After testing representative data, I would compare plans and P95 latency. I would also verify that the optimization preserves transaction semantics and does not create excessive write overhead. Focus on reproducing the issue, reading the execution plan, indexing selective columns, avoiding unnecessary scans, checking joins and statistics, measuring before and after, and preserving correctness under transaction isolation. Question 6. What is the difference between optimistic and pessimistic locking? Pessimistic locking assumes conflicts are likely, so it locks rows before modifying them and prevents competing updates. Optimistic locking assumes conflicts are uncommon. Each record carries a version, and an update succeeds only when that version remains unchanged. Optimistic locking usually improves concurrency but requires retry or conflict handling. For a high contention account balance, pessimistic locking may be safer, while optimistic locking suits lower conflict profile updates. In your answer, compare conflict assumptions, database locks, version columns, retries, deadlocks, throughput, consistency requirements, and examples involving concurrent account or payment updates. Question 7. How would you design an idempotent payment or money transfer API? I would require a client-generated idempotency key and scope it to the authenticated account. The service stores that key, request fingerprint, status, and final response in a durable store with a unique constraint. Retries return the original result instead of executing another transfer. The transfer and key state must change atomically, with explicit pending, succeeded, and failed states. I would reject reuse with different payloads and monitor stuck operations. Make sure to cover idempotency keys, request persistence, unique constraints, atomic state transitions, retries, response replay, timeout behavior, and protection against duplicate financial side effects. Question 8. How would you design a resilient microservice that processes transaction events? I would place transaction events on a durable message broker and let consumers process them asynchronously. Each consumer would validate the schema, apply the change idempotently, acknowledge only after durable completion, and retry transient failures with backoff. Poison messages would move to a dead letter queue for investigation. Circuit breakers protect downstream systems, while metrics, traces, and correlation IDs support diagnosis. I would document whether delivery is at least once and design accordingly. Discuss durable messaging, consumer groups, retries, dead letter queues, idempotent consumers, circuit breakers, observability, backpressure, schema evolution, and clear delivery guarantees. Question 9. Explain ACID properties and why they matter in financial systems. ACID describes guarantees for reliable transactions. Atomicity ensures all transfer steps commit or none do. Consistency preserves constraints such as balanced ledger entries. Isolation controls how concurrent operations observe intermediate state, and durability ensures committed data survives failures. In financial systems, these properties prevent partial transfers and incorrect balances. I would choose an isolation level deliberately, because stronger isolation improves correctness but can reduce concurrency or increase locking. Be sure to define atomicity, consistency, isolation, and durability, then connect them to ledger correctness, concurrent transfers, crash recovery, constraints, and appropriate transaction boundaries. Question 10. What is the difference between REST and messaging, and when would JPMorgan use each? REST is request-response communication, so it works well when a caller needs an immediate result, such as validating an account request. Messaging decouples producers and consumers, making it better for asynchronous workflows like transaction notifications or reconciliation. REST simplifies interaction but couples availability and latency. Messaging improves resilience and throughput but introduces eventual consistency, replay, ordering, and operational complexity. I would choose based on business timing and failure requirements. In your answer, compare synchronous request response with asynchronous communication, coupling, latency, delivery guarantees, retries, ordering, user experience, and suitable internal or external integration scenarios. Question 11. How do you prevent race conditions in concurrent Java code? I first identify which data is shared and which invariants must change atomically. I prefer immutable objects and thread-safe abstractions when possible. For compound operations, I use synchronized sections, explicit locks, or atomic classes such as atomic integer, depending on the contention pattern. Concurrent hash map helps with safe access but does not automatically make multi-step workflows atomic. I also establish consistent lock ordering, test under load, and measure contention before optimizing. Focus on identifying shared mutable state, atomic operations, synchronized blocks, locks, concurrent collections, immutability, visibility, deadlock avoidance, and selecting the simplest correct synchronization strategy. Question 12. How would you detect and resolve a memory leak in a production Java service? I would confirm the pattern by comparing heap growth, garbage collection frequency, pause times, and traffic. If objects remain retained after collections, I would capture a heap dump and inspect dominator trees for oversized caches, static collections, listeners, or thread local values. I would reproduce the workload in a controlled environment, fix ownership or eviction, and load test the change. Finally, I would deploy gradually with alerts for heap occupancy and GC behavior. Mention heap trends, garbage collection behavior, heap dumps, dominator analysis, retained references, caches, listeners, thread locals, reproduction, safe remediation, and monitoring after deployment. Question 13. What testing strategy would you use for a high-risk transaction service? I would use a layered strategy. Unit tests cover validation, calculations, and state transitions quickly. Integration tests verify database transactions, messaging, and external contracts using realistic schemas. End-to-end tests exercise critical transfer journeys, while property-based tests check invariants such as balanced debits and credits. I would inject timeouts, duplicate messages, and partial failures. Security and performance tests are essential, and production monitoring validates assumptions after release. Cover unit, integration, contract, property-based, end-to-end, failure injection, security, performance, data integrity testing, test isolation, and risk-based prioritization. Question 14. How would you secure an API handling sensitive financial data? I would authenticate callers using short-lived tokens and authorize every operation against account ownership and role permissions. TLS protects data in transit, while encryption and managed key rotation protect stored information. Inputs require strict validation, and secrets stay outside source code. I would apply rate limits, avoid logging sensitive values, and create tamper-resistant audit events containing actor, action, time, and correlation ID. Threat modeling and regular dependency scanning complete the approach. Be sure to discuss authentication, authorization, least privilege, encryption in transit and at rest, input validation, secrets management, audit logging, rate limiting, token handling, and data minimization. Question 15. Explain how a hash table works and how you would handle collisions. A hash table maps a key to a bucket using a hash function, then stores or locates the associated entry. Collisions are handled through chaining or open addressing. As the load factor rises, resizing keeps expected lookup near 0.1, although pathological collisions can degrade performance. In Java, keys must implement equals and hash code consistently. Equal keys need equal hashes, and mutable key fields should not change while stored. In your answer, explain hashing, buckets, load factor, collision resolution, resizing, expected complexity, poor hash functions, and why correctly implementing equals and hash code matters in Java. Question 16. How would you find the first non-repeating character in a string? I would count each character in a first pass, then scan the string again and return the first character whose count is 1. A linked frequency map can preserve insertion order, but two simple passes make the logic explicit. The time complexity is O(n) with O(k) space for the character set. I would clarify whether case and Unicode normalization matter. For a stream, I would maintain counts and a candidate queue. Discuss frequency counting, preserving original order, character encoding assumptions, one-pass versus two-pass approaches, complexity, and how requirements change for Unicode or streaming input. Question 17. What is the difference between a database index and a cache? An index is a database data structure that accelerates queries while remaining part of the database's consistency model. A cache stores frequently accessed results closer to the application for lower latency, but it can become stale or disappear. Indexes increase write cost and storage. Caches require expiration or invalidation strategy. I would use an index for reliable query performance and a cache for hot, read-heavy data with acceptable freshness. Make sure to compare purpose, durability, consistency, lookup speed, invalidation, storage cost, write behavior, cache-aside patterns, and examples involving customer or transaction reads. Question 18. How would you troubleshoot a service whose latency suddenly increased after deployment? I would compare latency before and after deployment, separating P50 from tail latency and checking error rates, throughput, CPU, memory, and database metrics. Distributed traces would reveal whether time moved into application code, queries, or dependencies. I would inspect changed configuration and execution plans, then reproduce using representative traffic. If customer impact is significant, I would roll back or disable the feature first, preserve evidence, and follow with a permanent fix. Cover deployment correlation, dashboards, P50 and P99 latency, traces, logs, resource saturation, database plans, dependency health, rollback criteria, and a measured root cause process. Question 19. Describe a time you disagreed with a technical decision and how you handled it. On one project, I disagreed with adding a synchronous dependency to a critical request path. I explained the latency and failure risks, then built a small comparison using production-like traffic. The team agreed to make the workflow asynchronous with a status endpoint and retry policy. I documented the trade-offs, incorporated feedback, and helped implement the decision. The result reduced tail latency and isolated downstream outages without blocking the release. In your answer, use a concise star structure, explain the technical evidence, show respectful collaboration, quantify the outcome, and demonstrate willingness to support the final decision. Question 20. How would you design a secure, scalable audit logging system? I would emit structured audit events containing actor, action, resource, timestamp, request correlation ID, outcome, and source service. Events would go through a durable pipeline into append-oriented storage with strict access controls and defined retention. Hash chaining or signed batches can expose tampering, while sensitive fields should be minimized or masked. Consumers can index copies for investigation and alerts. I would design for backpressure, replay, clock consistency, and failure visibility. Discuss immutable event records, actor and correlation metadata, schema design, centralized collection, access control, retention, integrity verification, privacy, searchability, alerting, and operational scalability. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.